Welcome to my workshop. I'm Jim. Today I want to share with you what I've learned about using NPN and PNP transistors in switching mode. NPN and PNP transistors are named after the layers of material from which they're constructed. An N-type of material is one whose atoms have a loosely bound electron in their outer layers. It doesn't take much energy to encourage such an atom to pass that electron along to a neighbor. Metals are an N-type material. The outermost atoms in a metal are very easy to move around. In fact, the difference between a metal and a semiconducting material is more a matter of degree than a black and white characteristic. Even the tiniest voltage will move electrons in a metal. In a semiconductor, on the other hand, there's a threshold voltage, in the order of a half volt or so, that has to be exceeded before the electrons move. A P-type of material is one whose atoms are ready and willing to accept an electron into their outer layer of electrons. NPN and PNP transistors are each made of 3 layers of N-type and P-type material. They're named after the order of those layers. The 3 layers make contact at 2 faces. These faces are called junctions, so NPN and PNP transistors are also called bipolar junction transistors, or BJT for short. NPN and PNP transistors can operate in different modes. What's a mode? We often think about a transistor as an amplifier, which takes a small input signal and amplifies it into a big output signal. This is called a transistor's linear mode. If the circuit works well, then the output signal will be a scaled-up version of the input. If the output is distorted in some way, then the amplification was nonlinear. Usually, a designer wants the scaling up to be linear, so that the output looks the same as the input, just bigger. The green arrow shows the main path taken by current flowing through the transistor when it's operating in linear mode. The input signal will add a bit of current, but the overwhelming majority of the current will flow in at the top and out at the bottom. Under some conditions, we can overload a transistor so that its main current pathway, shown here in green once again, becomes a short circuit. Short-circuiting the resistor that's shown is no big thing, but the output circuit can be more complicated. If it has its own supply of power, then short-circuiting the transistor will complete the external circuit, just like a switch. Under other conditions, we can manipulate a transistor so that its main current pathway becomes an open circuit. Even if the output circuit has its own supply of power, open-circuiting the transistor will prevent the external circuit from working. In this condition, where the main pathway is an open circuit, the transistor is said to be cut off. At the other extreme, where the transistor's main pathway is a short circuit, the transistor is said to be saturated. These 2 extremes are the cutoff and saturation modes of the transistor. If we set things up properly, we can cause the transistor to alternate between cutoff mode and saturation mode. If we do this, we can cause the external circuit to switch on and switch off. We would be operating the transistor in what's called switching mode, using it just like an ordinary single-pole switch. I should point out one thing. When it's used in switching mode, a transistor is not processing an alternating voltage like an audio waveform. Instead, it's acting like the on-off switch of a power supply. For this reason, it would be more precise to call switching mode a DC operating mode, where DC stands for direct current. This clarifies that the transistor is not processing an alternating current when it's in switching mode. Here are the symbols for an NPN and a PNP transistor. In a schematic diagram, transistors are usually given a name that starts with the letter Q. Q2 and Q5 would be typical names. The only difference between the symbols is the direction of this arrow on one of the 3 leads. The trick I use to tell one from the other is to imagine the letters NPN along the side, like this, and to note that the loop in the letter P points in the same direction as the NPN's arrow. The arrows have real meaning. Like they do in diodes, the arrow shows the direction in which current will flow when the transistor is operating in its linear mode. Current will flow from top to bottom in an NPN transistor and from bottom to top in a PNP transistor. It's usual in a schematic diagram for positive voltages to be at the top of the page and for negative voltages, or ground, to be at the bottom. In the same way that it's conventional to draw circuits so that signals flow from left to right, it's conventional to have voltages drop as one goes from top to bottom. The NPN transistor shown here is consistent with those conventions. Current flows through the main pathway in the same direction as the voltage drop, from top to bottom. But that's not the case for the PNP transistor, which is why the PNP transistor is very often seen the other way around on schematics. Usually, the lead with the arrow is at the top, like this. Then, the current in the main pathway flows down, in the same direction as the voltage drop. Let me describe the collector, base, and emitter. These are the names given to the three terminals of an NPN or a PNP transistor. The base is the one with the flat side. This is the lead that controls the transistor. The emitter is the lead with the arrow. The collector is the remaining lead. The green arrow shows the current flowing down through the main pathway of this NPN transistor. It's usual to use the letters C, B, and E as subscripts for any variables which refer to a particular terminal. For example, we would use I subscript C to represent the collector current. Of course, we wouldn't pronounce this as I subscript C. We'd pronounce it as IC. The base is the control terminal. Any input signal is injected here. The red arrow shows how the base current flows. It enters the base and flows out of the emitter at the bottom. The symbol one would use for this base current is I subscript B. In a similar way, the emitter current would be labeled as I subscript E. The sum of all the currents which flow into a transistor must be equal to the sum of all the currents which flow out of it. Otherwise, electrical charge would build up inside the transistor and it would be acting like a capacitor. It doesn't do that. So, the emitter current must be the sum of the collector current and the base current. Now let's work through the same process with the PNP transistor. The current through the main pathway is shown in green and identified as the collector current, I subscript C. The base current is shown in red. Note that the base current flows out of the base. This is quite different from the NPN transistor, in which the base current flows into the base. The emitter current must be the sum of the base and collector currents. Both types of transistor share this equality. I'm now going to describe the four characteristics of a transistor when it's operating in linear mode. I'm going to look into the conditions for linear mode because that's the easiest way to determine if and when the transistor is not in linear mode. Notice that I've removed the circles around the transistors. In olden days, when transistors were still new and exciting, these circles were always used, but modern schematics no longer show them. In linear mode, the base emitter junction is forward biased. That means that the P side of the junction is at a higher voltage than the N side. These blue arrows show the direction of the voltage drop over the base emitter junction when the transistor is in linear mode. Not only will the base emitter junction be forward biased, but the voltage drop over the junction will be 0.7 volts. I'm emphasizing the words will be 0.7 volts. In linear mode, the base emitter junction works like a standard silicon diode, in the sense that it has only one voltage. If the diode is conducting, the voltage will be 0.7 volts. If the voltage is not 0.7 volts, or is negative, then the diode will not be conducting and no current will be flowing. I've drawn in the two currents which flow through the transistors. The green arrows show the main pathways between collector and emitter. The red arrows show the base currents. The base currents are the ones which exert control. In linear mode, the relationship between these two currents is almost magical. The collector current will be 100 times the base current. Let the red arrows be the base currents. Then the collector currents, shown in green, are 100 times bigger. We can go even further. I've now shown the emitter currents in pink. Since the emitter currents must be the sum of the base and collector currents, then the emitter currents must be equal to 101 times the base currents. When a transistor is put into a circuit, we can always use these relationships to calculate the voltages and currents at the three terminals. Once we've calculated the voltages, we need to do a check. We will ask, is the base collector junction reverse biased? If it's reverse biased, then the transistor is operating in linear mode. If it's not reverse biased, then the transistor is not in linear mode. I've shown with these black arrows the direction that's required for reverse bias. Let's work through an example. Is this transistor operating in its linear mode? The direction of the arrowhead tells us that this is an NPN transistor. The base terminal is the one with the flat side. The emitter is the one with the arrow, and the one that's left over is the collector. In linear mode, the base emitter junction will be forward biased. Not only that, but the voltage drop over the junction will be 0.7 volts. Since the emitter is at ground potential, the voltage at the base terminal must be 0.7 volts. The 100K resistor is called the base resistor since it's connected to the base terminal. The voltage drop over the base resistor is 12 volts at the top, less 0.7 volts at the bottom, or 11.3 volts. We can now calculate the current which flows down through the base resistor using Ohm's law. The current is the voltage divided by the resistance, which is 11.3 volts divided by 100,000 ohms, or 0.113 milliamps. So the base current is 0.113 milliamps. We turn our attention now to the collector resistor. This is the 600 ohm resistor attached to the collector. We use the amplification factor for linear mode, that the collector current equals 100 times the base current. This will be 11.3 milliamps. Since we now know the current and the resistance of the collector resistor, we can use Ohm's law a second time to calculate the voltage drop over the collector resistor. Voltage equals current times resistance. 11.3 milliamps is 0.0113 amperes. Multiplying that by 600 ohms gives 6.78 volts. Calculating the voltage at the collector terminal itself is now just a matter of subtraction. Subtracting the voltage drop of 6.78 volts from the 12-volt supply voltage gives 5.22 volts. As the last step, we need to confirm that the collector voltage, which is 5.22 volts, is greater than the base voltage, which is 0.7 volts. It is, so the base collector junction is reverse biased. The answer to the original question is yes, this transistor is operating in linear mode. How about this transistor? Is it operating in linear mode? It's an NPN transistor as before, and the three terminals have the same orientation as they did before. This circuit is running off 5 volts, and I've changed the values of both resistors. In linear mode, the base emitter junction will be forward biased with a voltage drop of 0.7 volts. Therefore, the voltage at the base terminal will be 0.7 volts, so the voltage drop over the base resistor will be 5 volts less 0.7 volts, or a drop of 4.3 volts. We use Ohm's law to calculate the current flowing through the base resistor. It's 4.3 volts divided by 4,700 ohms, or 0.915 milliamps. Since the base current is 0.915 milliamps, the collector current will be 91.5 milliamps, which is 100 times greater. The voltage drop over the collector resistor, which I've highlighted with the red arrows, is this current multiplied by the resistance. 91.5 milliamps is 0.0915 amperes. Multiplying by the 166 ohm resistance gives a voltage drop of 15.2 volts. Therefore, the voltage at the collector terminal will be 5 volts less 15.2 volts, or negative 10.2 volts. That's not going to happen. The collector voltage will not be negative. Something must be wrong, but it's not our calculations. We used Ohm's law correctly, and we didn't slip up when using the calculator. What's wrong is the assumption that we made at the outset. We assumed that the transistor was operating in its linear mode. That turns out to be a bad assumption. It's not operating in linear mode. Instead, it's operating in saturation mode. A good question to ask is this: Although we've shown that it's not in linear mode, how do we know that this transistor is in saturation mode and not in cutoff mode instead? Well, here's how we know. The red and green arrows show the pathways for the base and collector currents. The base current is the one that exercises control. As it increases, the collector current increases. It's a bit like a tap. The more you open the base tap, the more water flows through the collector. But like a tap, it has a maximum. Once it's fully open, that's it. All the water that can go through is going through. There's no more. And that's what's happened here. As we reduce the value of the base resistor, more base current flows. We've reduced the value of the base resistor so far that the transistor has maxed out. Once it's reached the saturation point, the transistor then acts as if all three terminals are shorted together. Therefore, the voltage drop over the base resistor is the full 5 volts. So is the voltage drop over the collector resistor. It's then a simple matter to use Ohm's law to calculate the currents flowing through the resistors. The base current is 5 volts divided by 4,700 ohms, which is a little bit more than 1 milliamp. The collector is 5 volts divided by 166 ohms, or 30.1 milliamps. Let's do one last example. I've moved the 4.7K base resistor down so that it's now tied to ground rather than to the 5-volt supply. Unless some current flows through the base resistor in either direction, the voltage at its top end must be the same as the voltage at its bottom end, namely ground potential. For this to happen, current must either flow into or out of the base terminal of the transistor. Current will never flow out of the base of an NPN transistor, and current can flow into it only if the voltage at the base terminal is higher than the voltage at the emitter. But since there's no independent voltage source at the top of the base resistor, the only possibility is that there is no current flowing at all. Therefore, the voltage drop over the base resistor, shown here with the red arrow, must be 0. So, right off the bat, we failed the first two criteria for operating in linear mode. This transistor cannot be in linear mode. Since there's no base current, it can't be in saturation mode either. It's in cutoff mode. In cutoff mode, the transistor acts as if all three terminals are open circuits. No current flows through the base terminal or through the collector terminal. Since no current flows through them, the voltage drops over the base and collector resistors must be 0. The voltages at the base and collector terminals will be 0 and 5 volts, respectively. I'm now going to put together a real switching circuit using this 2N2222A transistor. I'll connect the same 4.7K base resistor and the same 166 ohm collector resistor as before. The top of the collector resistor will be connected to a 5-volt supply, but the base resistor will be connected differently. The driving signal for the base resistor will be a square wave. The square wave will alternate between 5 volts and 0 with a period of about 4 seconds. It will be on or high for 2 seconds and off or low for 2 seconds. The transistor will switch between saturation mode and cutoff mode. The current through the collector resistor will alternate between 30.1 milliamps and 0, as we previously calculated. When the driving voltage is high, the transistor will saturate. The maximum amount of current will flow down through the collector resistor. That's 30.1 milliamps. When the driving voltage is low, the transistor will be cut off. No current will flow through the collector resistor. Now, in the real circuit, I'm not going to use a standard 166 ohm resistor. Instead, I'm going to use a 5-volt relay. When somebody says that a relay is a 5-volt relay, they're talking about the voltage drop over the coil, which will close the contacts. They're not talking about the voltage that the relay's contacts can handle. That can be different. The relay I'll use is DigiKey's part number PB1017-ND. The datasheet tells us that this relay's coil resistance is 166 ohms. That's the resistance of the wire from which the coil is wound. When 30.1 milliamps flows through the coil, the contacts will close. This relay happens to be a single-pole double-throw relay. Since it's a single-pole relay, there's only one movable contact. NC stands for normally closed. When the coil is not energized, the normally closed contact will be shorted to the movable contact. If there happens to be a circuit connected between the normally closed contact and the movable contact, it will be completed. The other contact is the NO contact, which stands for normally open. When the coil is energized, the movable contact will be shorted to the normally open contact, and any circuit connected between them will be completed and start to operate. This shows the external circuit that I'm going to use. It's simply a 60-watt incandescent bulb plugged into a 120-volt wall outlet and using the normally open contact as an on-off switch. The bulb will turn on and off in step with the transistor as it switches between saturation and cutoff modes. I've wired up the circuit on a breadboard. Power for the circuit comes from a 5-volt DC power supply, which I've placed several feet away so that its noise doesn't affect the soundtrack. When I insert this red wire, like this, the circuit will go live, and the 60-watt incandescent light bulb will start to flash. I've soldered wires onto the base of the light bulb, one here along the rim, and a second here at the bottom beneath the threads. These wires let me plug it into the breadboard. This is the power cord. It's plugged directly into a 120-volt outlet on the wall. Yes, these are all exposed 120-volt wires, but I'm taking care not to let my hands touch anything. This is the relay. It has 6 pins, but they're not arranged in the same 1/10 of an inch square grid as the holes in the breadboard, so I've had to solder short extension wires on in order to insert the relay into the breadboard. This is the 2N2222A transistor. It's a great transistor for general purpose use. It can be used in circuits with voltages up to 40 volts, and you can run up to 800 milliamps into its collector. This metal can is called a TO18 package. This is the 4.7K base resistor. The square wave driving voltage is generated by this 8-pin dip, which is a 555 timer chip like those I've described in previous tutorials. It's running in continuous mode. I selected this 100 microfarad capacitor and these 2 timing resistors so that the output from the timer, which is available here on pin 3, is high for about 2 seconds and then low for about 2 seconds. The 4.7K base resistor carries the square wave from pin 3 of the chip over to the base terminal of the transistor. You may have noticed that when I inserted the red wire, it took a couple of seconds for the timing capacitor to charge up and begin the flashing of the light bulb. You may actually be able to hear the contact inside the relay switching on and switching off. Good, that's all. Let's rig up a PNP version of the light flashing circuit. We'll move the relay and the load circuit from the top of the schematic to the bottom. In the NPN version, the top of the relay's coil is connected to the positive 5-volt supply. In the PNP version, the bottom of the relay's coil will be connected to ground. In the NPN version, the transistor controlled how much current flows out of the bottom of the coil. In the PNP version, the transistor will control how much current flows into the top of the coil. Of course, the transistor will have to be a PNP version. The base will be in the same place, but the collector and emitter terminals will be switched top to bottom. I'll use a 2N4403 transistor. It's similar to the 2N2222A. They both have working voltages of 40 volts. The 2N2222A can handle up to 800 milliamps of collector current, but the 2N4403 can only go up to 600 milliamps. It's quite common to see PNP transistors which have slightly more limited capability than their NPN counterparts. That's because our universe runs on electrons. N-type semiconductor material, which is based on the movement of electrons, is more efficient than P-type semiconductor material, which is based on the movement of missing electrons, or holes. Note that the two circuits don't operate in the same phase. The red square wave is the output from the 555 timer chip. It's the same for both circuits and is applied to the left end of the 4.7K base resistor in both circuits. When the timer voltage is high, the base emitter junction of the NPN transistor is forward biased and the transistor will go active. In fact, the values of the resistors are such that the maximum amount of current will flow and the transistor will go into saturation mode. When the timer voltage is high, the PNP transistor, on the other hand, will behave differently. During this period, the voltage at both ends of the PNP's base resistor will be 5 volts, so it will be in cutoff mode. When the timer voltage is low, both ends of the NPN's base resistor will be at ground potential and it will be cut off. During that time, when the timer voltage is low, the base emitter junction of the PNP transistor will be forward biased and the transistor will go active. The maximum amount of current will flow and the transistor will go into saturation mode. It follows that the light bulb will flash in alternate half cycles in the two circuits. This is the PNP circuit in operation. I made only 3 changes in the wiring to convert the NPN version into this new PNP version. These 2 wires were exchanged so that this end of the relay's coil is now grounded and the transistor's emitter over here is now tied high. And of course, I changed the transistor. This is a 2N4403. It has a different package than the 2N2222A. This one's called a TO95. But they both have the same pin orientation, so that I was able to plug the PNP transistor into the very same holes on the breadboard as the NPN one used before. Everything's working as it should. One often hears about a transistor's beta. What's beta? Beta is the second letter of the Greek alphabet. It's equivalent to our modern B for Bravo. Beta is related to the magical relationship between the collector current and the base current in bipolar junction transistors. We've used the relationship that the collector current is 100 times the base current. That means that the collector current is equal to the base current amplified by 100. This factor, 100, is the transistor's beta. To be precise, we should add a subscript DC to make it clear that this is the multiplication factor when the base and collector currents are constant, or DC. The multiplication factor when the transistor is amplifying alternating currents can be slightly different. You won't see the symbol beta in a transistor's data sheet. Manufacturers use a different symbol, HFE, when reporting the DC beta. Beta is not always equal to 100. It can even vary from one transistor to another in the same batch of part numbers. However, 100 is a very good place to start for any medium-sized general-purpose transistor. For a large power transistor, beta will be lower, probably closer to 30. For a small high-gain transistor, beta could be 500 or even more. A quick look at the datasheet will provide the beta, or range of betas, for any transistor of interest. Let me also say a word about a parameter called the saturation voltage. The symbol Vsat is used for the saturation voltage. I said above that a transistor in saturation mode could be treated as if all 3 terminals were shorted together. That's a good first approximation. Sometimes, however, more accuracy is needed. When it is, look at the base collector junction. In both types of transistor, NPN and PNP, the current which flows between the base and the collector must flow out of an N-doped material and into a P-doped material. The blue arrows point from the N-type material to the P-type material. From the point of view of voltage potentials, this is an uphill climb, and a bit of voltage is lost climbing up through the barrier at the junction. We can improve our model for saturation mode by including this little bit of reverse voltage. I've shown it here as a small battery whose nominal voltage is Vsat. Vsat opposes the flow of collector current in both types of transistors. When we do our calculation for the voltage drops in the collector branch, we will allow for this small voltage drop. How small is the voltage drop? For a typical general-purpose transistor, Vsat is likely in the range between 0.2 volts and 0.4 volts. For a transistor advertised as a switching transistor, which is intended for applications where it switches between saturation mode and cutoff mode, the saturation voltage will be less, likely 0.1 volts or so. In addition, there are transistors made especially for saturation mode, which go even lower. Once again, the datasheet will report this parameter for any transistor you're interested in. I'll conclude by tying up a couple of loose ends. The square wave voltage, which controlled the test circuits above, was generated by a 555 timer chip. I didn't go into the details because there's a previous tutorial about this chip. The timing is governed by three external components. Resistor RA is 510 ohms, resistor RB is 25K, and capacitor C is 100 microfarads. These components result in a square wave which is high for 1.77 seconds and low for 1.73 seconds. The 2N2222A transistor comes in a TO18 package. It's a metal can with a tab jutting out from the bottom of the can. The emitter, base, and collector leads are arranged in a semicircle in that order, starting with the emitter closest to the tab. Whether you look at the transistor from the top or from the bottom, it's easy to tell which lead is which. The 2N4403 transistor comes in a TO95 package. It's a plastic cylinder with a flat side. The emitter, base, and collector leads are arranged in a straight line, in that order, parallel to the flat side. However, the order of the leads will appear to be different when looking at the transistor from the top or from the bottom. Although emitter, base, collector is a common order for the three leads, it's by no means universal. Always check the datasheet for the lead positions before inserting a transistor into a breadboard or laying it out on a printed circuit board. This is the pinout given in the datasheet for the relay I used in the light flashing circuit. This is the top view. The coil has been drawn using the symbol for a resistor. The pinouts for relays are always shown with no current flowing through the coil, which is to say, in the unenergized state. We can therefore tell that the normally closed contact is the one at the upper left, and the normally open contact is the one at the lower left. There are two pins for the common contact, one on either side of the component, to make it easier to wire into a circuit. That's all for today. Thanks for watching. See you next time.